Hello, everyone. In today's Zoom lecture, we'll be talking about the rise of the anthropoids. This is part 2 in our 3-series unit on primate evolution. All right, so let's do a share of our PowerPoint and get going. So a little review from our last section. We talked a little about what's happened in the past and why it's happened in the past. What you're looking at here is a very simplified chart of world global temperatures over the Cenozoic. This is an average mean of all the temperatures and the shifts from the very beginning at about 65 million years ago, at the beginning of the Paleocene, up to the current time right now in the late Holocene. So as we saw before, primate evolution begins with the appearance of point A, Purgatorius, our first proto-primate. And from that point, it proceeds on to the adaptive radiation of the pletiodiapic forms, where are gradually, acquiring more primate characteristics. And as they continue to evolve, we start getting a rise in temperature. And as we hit just around the 54 million year point, we get the establishment of the first true primates, which we refer to as the euprimates. And those differentiate into two subtly different groups, which are known as Adaptoids and Omimioids. The Mimoids continue to evolve till they arrive into two relatively distinct groups. The Adaptoids become strepsirrhines, the Omimioids become haplorhines. Strepsirrhines go off on their own evolutionary trajectory, which we'll talk about at some point in the course, not right now, to produce living lemurs, lorises, and bush babies. The Omimioids will go on and do a transition that occurred just about 45 million years ago. And that transition will be one group will break off into just tarsiers, and the other group will break off into what are known as the anthropoids. And there we can see the anthropoids. Now, if the chart that I have there where you see the line on the anthropoid in the top, at that I mean at the point in which we have actual true anthropoids. And at about 44 million years ago, 45 million years ago, anthropoid evolution begins, and we're going to be going through a period of transition, just as we did when we established the first sort of primates. And that transition will be driven by factors in the environment and other issues, which we'll be talking about a little later. But suffice it to say that the anthropoid group is constituted by old world monkeys, new world monkeys, all of the apes, and humans through evolutionary time. Okay? So the last time we're talking about is the appearance of Adaptoids and Mimioids due to this global expansion of fruit growing, of flowering tree growing plants all over the world because of warming temperatures up into high latitudes. We get a lot of population because of that, not only in the trees, but also in the primates. And one of the rules of evolution is the higher the level of population, the more mutations you're going to produce that are available for evolution to use to change a population. If you think about it, one change in an individual is not going to modulate, a population as much as if you've got, a million individuals, a lot of changes being produced. That creates very quick adaptation up to into environments. So we're getting a massive adaptive radiation in many, many different forms of primates during this period of time, which we'll look at. And that radiation continues up into just about the point in which we get a little bit past point E on our diagram, and we enter a period of pulse extinction, known as the Grande Coupure. And we literally shear off, oh my God, we're 31 groups of primates we're going to lose, and only 5 groups are going to be remaining. So we'll be looking at what happens during that period of pulse extinction. And in the aftermath, how do the anthropoids continue to develop, and what sort of anthropoids do we see? First thing to look at is the beginning of anthropoid evolution, and a little bit about what the plate tectonics had the continents at in this period of time. So we're looking at a snapshot of the late Eocene, approximately 35 million years ago. At this point in the world, anthropoids had been evolving for roughly 5 to 10 million years. Anthropoid evolution really began about 45 million years ago with our first fossil evidence of making the transition. And that occurs in the Arabian Peninsula, mostly in the southern Arabian Peninsula, as well as where southern China is. And there are illustrated on this diagram, put 2 little yellow loops down there. As evolution of anthropoids begins to continue through time, we get a movement of anthropoids in a northwest sort of direction as they move through peninsular, an island, the Mediterranean, or what is Europe today. This is exactly the shape of it. And that radiation continues. And finally, what will happen is the primates will make their way into Africa. Now, by about 40 million years ago, primates are in a position of just about where Pakistan now is. It's very difficult to locate, where Pakistan is here. But think about it, it would be on the upper end of the little balloon here with the central channeling. And we find anthropoids in the fossil record dating down to around 39 million years ago in Africa, particularly in Libya, where currently Libya is. By 31 million years ago in Egypt, we find really well-formed anthropoid fossils. I mean, they have all the characteristics of anthropoids. They've gone through their 9 million year transitional period. What we think in many situations here is that the earliest anthropoids that get in to Africa continue their evolution in Africa and become those well-formed anthropoids which we see in those deposits. Of course, we're going to continue to see influx of other anthropoid forms into Africa. There's going to be a residence, a migration will move in and out. But in many respects, we feel that the original inhabitants that moved in could very well be the ones that evolved in situ that continue on the evolutionary heritage that actually occurred in Africa. This puzzle is still being worked out. We're still analyzing the fossils, but I'm going to present to you what we have and the model we have behind it to talk a little bit about our heritage today. Now, last thing I want to say about this diagram, if you're noticing, this is a snapshot of Earth at that period of time, and that does not look like the Earth today. This continual continental movement is something that just has happened. But that continual continental movement that's happened in the Eocene that progresses all the way to now has changed everything for conditions in Africa, everything conditions in the world, that has driven primate evolution. So let's figure out in what ways it has. Well, one of the things we're going to think about and how evolution can actually affect us are the dire consequences of continental changes and movements around the world. As continents are moving around the world, they change global flows of air. They also create mountain ranges. So when you look back at diagrams like this, at this period of time in the Eocene, there were no Alps. The Ural Mountains aren't there. The Himalayas aren't there. And as Africa begins its trip and pushes it more north and eastward, through continental rifting, you can see the little line in the Atlantic right down to the little light streak that goes down the Atlantic. There's not a wave. That's actually supposed to illustrate that there's a rifting zone, right? So that is actually the Earth welling up and splitting apart and spreading, a spreading point, pushing South America out to the west and forcing Africa over to the east and to the north. Well, the same thing is happening with India, but India is just going straight forward up north. This is just beginning to happen. So progressively, as these continents begin to collide, the compressional forces are going to cause eruption, the uplift of mountains. So we're going to get all the mountain ranges. And when that happens, it changes the global flow of air and moisture. And it raises all get out on Africa and changing the environment constantly, the ecosystems which we see they're putting on all sorts of different pressures on primates for selection. And we're going to get a rapid diversification of anthropoids, all sorts of forms which you see today, all the monkeys, all the apes, and of course, in humans. So we'll be paying attention to more of this and I'm explaining how that happens later. So first of all, if I want to think about this chart again, now that we know that how much change can actually happen from the global, movement of continents, what can they produce? Well, one are called extinctions. This is the result of a pulse extinction, which we saw earlier in the diagram, which we labeled as the Grande Coupure that happened just about 34.5 million years ago. And at that point, we get a severe global decrease in temperature. The disruption in habitat in which that caused eliminates 31 large groups of primates, 31 large groups. And of course, each one of these large groups have taxons, they're the genuses which are involved in them. Let's think about 31 large groups and what's left today. Today on Earth, we have the 5 surviving groups of the Grande Coupure. And there they are. Anything without a red line above it, it survived. Anything with a red line on it is out. So what do we have today? I can see we have lorises, Lorisidae. There's 5 genera of those by taxa. We have lemurs, Lemuriforms, there's 6 of those, and Galagidae, which are bush babies. I always get left out on many of the schematics here. We don't want to forget about bush babies. They're there, so that's 3. What else do we have? Well, we have tarsiers. That represents the 4th group. and we have anthropoids. So anthropoids are a combination of Old world monkeys, new world monkeys, apes, and humans. And why are they grouped together? Because we're far more similar than different, as we shall see in the course. So 5 groups are remaining, 31 gone. Well, I love charts like this because they can give a little refresh on evolutionary history and what's happening too. So we can start down at the bottom. So there we have 65 million years ago, we get our first primate ancestors, right? The transition from purgatories to completed ape forms, and bam, what do we have? The establishment of the first hominoids and the first Adaptoids, in which you can see on the chart, the green line up indicates the hominoid line. The Adaptoids consistently radiate on out to create the group, the solid group called the Strepsirrhines. And all of those groups which you see that go extinct 34 million years ago are well-formed Strepsirrhine primates. Out they go. So on the hominoid line, as we move up that line, they make a transition to more solidly defined group called the Haplorhines. And then we have a split in the haplorhines that occurs at just about 44 to 45 million years ago, and tarsiers create tarsiforms in one direction, and the anthropoids go out in the other direction as well-formed groups, and they're also make it too. We got to figure out, which ones made it and why. I think that's very important. Let's go back to look at our look at the late Eocene. And this is just taken at just about the time in which the Grande Pour is about to occur, where we're going to get this global decrease in temperature as our continents begin to move and change global airflows. And there's some of the things that are happening with our trajectory around the sun and some of the orbital variance is happening too to bring this effect on. But for primates, what's going on? And why are they going extinct? Well, at this period of time, primates are in a few places. By 35 million years ago, we have some of the anthropoids there in Africa, as well as the rest of Eurasia. Because Eurasia is a continual continental mass. Notice from the very top of Asia all the way down to southern China and through the bottom of India. So the bottom of India actually touches the equator, which would definitely be the warmest parts on Earth. There's an unbroken passage that primates can travel. So during a cold snap, when we're decreasing, habitat, migration pathways there are that prevent extinctions. This is not true for North America. For North America, as the continent gets, as this proceeds, as Grande Coupure, if anything, it strengthens something that's part of our climatic heritage here, which is called the jet stream. One of the things about the jet streams is it dips down in sort of a U-shaped pattern, a strong trough through the United States. I mean, it misses Southern California and Florida a little bit, but as it troughs down, boy, does the center part of our country become extremely cold in the wintertime. While we're on relatively the same latitude as Kansas, imagine how much colder Kansas and Nebraska are than here. And try to magnify that and think about, what it would be like to be a primate. And you're depending on the growth of fruit and not, a few months in the summer, but continually throughout the year. When you're having, highly seasonal, it will create a strongly seasonal effect between maybe a short summer and long cold winters. The disruption in that habitat is going to reach so much havoc, you're going to end up with groups of primates going extinct. It can't migrate. There's no going up, the temperatures prohibit, as well as going down. Notice what's happening in Central America. We've got a pretty large strait system that's between Central America and the tail end of North America. I don't know if you've ever been to Washington, the Washington state of level where San Juan de Fuca straits that separate us from Canada, but that strait is about 5 times as long as that. You're looking at about 80 miles to 100 miles of water, deep water, where there's no island system. There's no possible way that our primates are getting across there. So literally, as the cold weather moves down upon them and changes the ecosystem that far down south, they cannot make that additional 1,500-mile life-saving journey into South America. Thus, all of the primates, all the groups that are primates that are in North America go extinct. That's it. Thus, the engine that fuels all of our evolution now is centered in the continent of Eurasia at 34 billion years ago, 34 plus million years ago, earlier to us, right? Now, primates at this point are not in South America. So since primates have never been in South America, they could not have come from North America. Therefore, that whole world has been sterilized from primates. If anything, it has to be recolonized or colonized for the first time, as we will see in South America soon. Now, So when we talk about these mass extinctions, we talking about, how, extinctions work and who makes it or who don't. I think it's a natural selection is only part of it. A lot of time catastrophe just happens, and being at the right place at the right time or being at the wrong place at the wrong time portends a lot to species survivability. And sometimes it has nothing to do with the ability to adapt. The strength and the forces of nature are so strong that then again, it just becomes by happenstance sometimes, in a way in which you could be struck by a meteor in your region at any time, which we're going to, which really how the Cenozoic was produced anyway, that can determine whether you're going to live or you're going to die. That's just the nature of life in itself. All right. All right, so now let's talk about the anthropoids, the ones that do survive, the 42 taxa. How do and why do they evolve? What are the reasons for anthropoids? And how do they make viable transitions to, full-blown monkey body plans into the separate different monkey groups, the old world monkeys, new world monkeys, finally into the apes, and then, of course, the final step into the higher level, or as we consider humans. All right. So one of the things we got to think about when talking about, well, why us and why anthropoids is the relative success of being an anthropoid. And we'll talk about the particular characteristics of an anthropoid a little bit later, but I want you to get excited about the success. Now, here is an evolutionary plot, and the thickness of each one of the representative groups talks about the success. That's the population, that's how many individuals that are there, their relative proportions. So we start in the Paleocene, and a lot of different groups are trying to get into the trees. A lot of groups of mammals, things like tree shrews and other groups. And they're, hopefully accumulating mutations that allow further and further adaptations to get into the tree, but they're going to let you one, right? One organism per niche. So Placididae performs a win the day, as we've seen. They make that little change, which goes very early on from Purgatorius, way back down earlier in the Paleocene. Placididae performs have a pretty good show. They're doing fairly well here until they split off into more well-formed forms, the true primates, the Amymioids and the Adaptoids. Because the Adaptoids and Amymioids do so well, they put Placididae perform as the remaining ancestral population out of business, the way evolution goes. Now, the Amymioids and Adaptoids work well in the early part of the Eocene. They continue on and they begin to branch. The Amymioids branch off into tarsiers roughly around 45 million years ago. And then slowly, they make a slow transition at about 45 into full-blown anthropoid groups, which we see, really firmly developed by about 33 million years ago. And once that happens, once all of the anthropoid characteristics together, look at that success compared to the success of the other groups which are out there. The massive numbers of anthropoid dwarf tarsiers. They dwarf the lemurs, lorises, and then the line for galagos can't even see the bush beavers aren't even on there, right? So to be an anthropoid means a successful, journey, evolutionary journey in the world, where tarsiers, lemurs, and lorises is marginal. In fact, lemurs themselves are only here today because they live strictly in an environment of Madagascar, where there are no anthropoids. Well, until recently. The recent invasion of humans and the pets in which we are bringing the lemurs to extinction simply because they cannot compete with us. We are a much improved form. Let's figure out what those improvements are and what they portend to the rest of the evolution and development of other primates. So we have to pay attention to the taxonomy. I think by osmosis, I want you guys to learn this. And it's important for us to visualize. Taxonomy gives us groups to think with, important groups. So I've shown you this before in primate beginnings, but let's do it again and get more refined to where we are, within our transition to anthropoid. So we know we have primates, the beginning of primates. That's our order. 65 million years ago, that was established. Then we transition into two nascent groups, the Amymioids, and we get the full-blown suborder haplorhine established. That's our suborder. So we're haplorhines. The Adaptoids, make this transition and they become a full-blown group. The Strepsirrhines, that's our suborder. That's not our suborder, that's part of primate suborder. The Strepsirrhines go off on a different direction to produce the infraorder lemuriform, that's all lemurs and lorises, and they split out into two superfamilies, the Muridae and Loricidea. And those are the lemurs and lorises. Bush babies should be in there too. And that's it. They have a pretty, that's about as extended of a much branching that they've done. Okay. And those are considered our prosimian groups. And we're not going to worry too much about them. When we talk about their characteristics a little bit later, in course, in living primates, we'll do that in a couple of weeks. But for right now, let's look at the haplorhines and what happens. So we were established as haplorhines solidly by 47 million years ago for sure. By about 45, we make another transition. The tarsiers split off into their own group, the tarsiforms, and the anthropoids, something truly anthropoid, begins to develop, establishing our infraorder, Anthropoidae. And that includes all the monkeys, apes, and us humans. So you and I are anthropoids, along with all the apes and monkeys out there at this point. Well, after anthropoids go through a lengthy period of evolution and time, they split off into two groups. And mostly it's because of a physical barrier that developed between them. One is the movement of South America away from Africa, and that dragging of one population of primates, the monkey groups apart, will create two separate groups eventually through genetic drift and some natural selection going on to create a group which we call the New World monkeys, and the parv order that's officially Platyrrhine. And then the Old World monkeys, which remain in Africa as well as in parts of the Middle East, Indonesia, and some select areas of Japan. We produce the Old World monkeys, the Catarrhine. And we'll talk about the diacritics. What are the characteristics of these groups a little bit later on. But I don't want to overload you with those things. I want to give you a little feel for what you should be thinking about in the taxonomy. Now, today we're going to be looking specifically at the infraorder, how we established the infraorder Anthropoidae, how we made a transition, how that split occurred between the Catarrhine and Platyrrhine groups, and a little bit about how we're starting to move into the superfamily. What were the first moves into the superfamily Hominoideae, the first apes and humans? This is what we're talking about, the rise of the anthropoids. Now, in module 4, we're going to change the tempo a little bit and look at the transition, in lecture 3 of the course. Before we go to module 4, we'll be looking about the transition of these anthropoid groups into the next important groups of our superfamily, Hominoideae, all apes. And we'll be looking at that a little bit later on. All right, so now let's continue our journey in the rise of the anthropoids. All right, so I used to work across the street from this guy named Chris Beer. He is now the director of vertebrate and paleoanthropology at Carnegie Mellon University in Pittsburgh. Very prestigious museum, a really fabulous place. It's actually in a little borough called Oakland. And my office was in the University of Pittsburgh, where I used to work. And I got to know him really quite well. And here's a quote from him. So he says this, he says, "We believe when these first anthropoids got into Africa, it was almost as if they had won the lottery." There's something special about the entrance to Africa. And also tells us something too, that anthropoid evolution did not happen first in Africa. It happened outside of Africa, as I mentioned. It happened in two places which are geographically very close to each other. The Southern Arabian Peninsula, of course, down by the equator, right? And Southern China, which still is very low in latitude. So the center of primate evolution, or anthropoid evolution in these areas. And from 45 million years old since it began, progression has been a migration through what is the peninsular Mediterranean area of that time, as we can see, and into Africa. And once they reach Africa, there's something special about Africa that allows some interesting changes that give rise to other forms of anthropoids. Okay. So the first anthropoids, let's talk a little about them. Well, why anthropoids first? Well, one thing that we see, if we look at the climactic profile of the period when anthropoids are evolving, and let's go back and have a quick look at that. It's worth looking at this, okay? So we look back at just about the middle of the Eocene at 45 million years ago. Anything on, we're starting to get a decrease in temperature. That's cooling and it's drying. There's going to be changes in the habitat as a result, and thus there must be changes and adaptations in primates, at least one group of primates. Remember, there's the Strepsirrhine group. They're going to have their own independent changes. Then our group, the Haplorhine group. Haplorhines are traditionally, at this point, diurnal at this point, and eating lots of fruits and insects. So when we think about fruits and insects, the types of foods that we're eating are purely arborable. They're in the canopies. Thus, the first thing that happens is a retraction of the spread, or the actual diversity of flowering plants and fruit growing plants. Thus, they're not growing at high latitudes. We get a decrease in them. Okay? So habitat retraction is one thing. Habitat retraction is one thing. Still, in the middle latitudes, we have enough. There's enough to continue with their anthropoid evolution. But it does portend changes because fruits become a little bit more seasonal. They're not so much staged and fully, 24/7, tropical rainforests that are going all the time. There's some seasonality that tends to happen. Rainfall becomes short in some areas. So there's adaptations to trees by producing, thicker integument fruits. The growing seasons are shorter. So primates have to begin to eat unripened fruit, developing bigger masticatory apparatuses. Additionally, nuts have to be consumed. They have to be utilized as food supplies, acquiring, again, more masticatory apparatus, more stronger jaws and facial features. And additionally, something else is going on too, the continual evolution of trees. Remember, trees, the number one source of energy in which they're looking for, the only source is sunlight. So the battle for ever increasing trees is continuing. The distance between branches is continuing, requiring stronger, larger bodies. And this is exactly what we're going to see, a progression of those traits as that cooling and drying increases. Until everything becomes, visible in a primate body, the anthropoid body, all these traits by about 33 million years ago. And then we'll see, subtle changes from that point on. Right? So let's go back to that slide again and look at the things that are happening. So as I mentioned, the first two anthropoids, let's think about that just about 33.9. And we get a lot of evolution since that, but we're looking at all the traits we're going to be talking about soon. They're going to appear in a well-formed body by about that period. Okay? And again, as I said, that the molecular evidence suggests this, that the full-blown anthropoids we're going to see at 33.9 million years ago began in Africa in many respects. Those are the early ones that got in, the ones that came from the areas of southern, Arabian Peninsula, as well as southern China. They began at 45 million there. They began to get in to Africa 40 million years ago. We have direct fossil evidence in Libya at 39 million years old. And it appears that many of these forms remained in situ, continue developing, and they take over anthropoid evolution in Africa and continue developing and radiate back out into the world. Now, the anthropoids that we see evolving in Africa, and we'll see eventually we'll have to split out into different groups, and the different groups will be, old world monkeys and new world monkeys. So the ones we're looking at right now predate that split. We'll be looking at the very earlier ones, and then we'll look at the evidence we have for that split and what sort of results we have. So we're back to the Oligocene Earth now. So it's very similar in some ways to the end of the Eocene. Africa is getting a little bit closer to what's happening, to the margins of Europe, I guess, closer and closer, and it will eventually, close that door. But it's also a period in which Africa's been separated from the wind of evolution for so long that many species that exist out there in the world, many of the large predators aren't in Africa. Like when we think about, tigers and big cats that are in Africa, they're not originally from Africa, they're imports. They're imports from, Asia. That once Africa made contact, with the continent of Eurasia, those big predators entered Africa. So it is an interesting and wonderful time again for these first, anthropoids that are there, because they're without a lot of heavy predation. Therefore, they can develop pretty fast, adaptive radiations without being checked in those niches. So other anthropoid adaptations, and I mentioned this. But we know that cooling and drying phase is going to lend towards, hard and more brittle foods. Additionally, leaves too. Leaves become important because leaves have more thicker, more woody stems that have to be sheared off. And leaves can be more thick and waxy, particularly in deciduous stuff. So we get more thick leaves and harder to chew sort of foods. So that means we're going to get more powerful jaws. So we're selected for stronger and more stable jaws. Now with this, we get another adaptation too. Anthropoids with a larger body plan are heavier. They're a larger mass, right? And additionally, with that larger mass, they're in bigger trees, which means to fall out of these trees means a bigger hit and bigger potential injuries to your skull. So in order, the first level is in order to protect that, we need a new structure in the eye, and that's called the enclosed eye orbit. So what anthropoids do is they evolve a completely enclosed eye orbit, bony. So if you took your eyes out, don't do this, or it will hurt you. You could feel back there, and there'd be a completely enclosed bone. Now, if you pull the eye out like a strepsirrhine, lemur, loris, a bush baby, there is no bony enclosure. You can put your fingers all the way back to the brain. Same thing with your dog. Be careful with your dog. Put your dog's eyes out. Put your finger back into its brain. Now, as I mentioned earlier, there is no adaptation in nature that has a single function. Neither does the enclosed eye orbit. Let's think about this. The enclosed eye orbit provides protection. It does strengthen the skull. It also does something else. As you're moving through the canopy, anthropoids have a unique adaptation, and that, they even bring their eyes further out, right? Full stereoscopic vision. When you look into the eyes of an anthropoid, they're far more stereoscopic than a strepsirrhine. Both have stereoscopic vision, but this is really frontal, right? Your facial eyes are very much like monkeys and other apes out there. Okay? And that's because of an adaptation to moving in environments which can kill you, which are lethal, and which you have to judge depth perception very well. And you also have to have quick vision. So notice this, if you turn your head really fast and look at something, how long does it take both your eyes to focus on something? It's almost instantaneous, because the bony eye enclosure back there allows for the attachment of muscles and ligaments, lots of them, for precise and fast movement of your eyes, visual acuity, very fast visual acuity. So for protection and fast visual acuity, overall strengthening of the skull. So enclosed eye orbits. Additionally, another feature that anthropoids have, and another reason for it to actually increase the strength for chewing, is if you look at other animals like the lower level primates, like strepsirrhines, lemurs, loris, and bush babies, or any other mammal, their jaw, which is called the mandible, is in two pieces. It just has a piece of cartilage together. It's pretty strong, but it's a piece of cartilage down that brings them together, and it stays that way throughout their life. This is not the case for anthropoids. All anthropoids, it's fused. So what happens is when it's born, there might be a little joint between it, but it quickly fuses over into a single bone. And that thing is called the mandibular symphysis. That's really what it is. When you're young, there's a little symphysis there. And of course, it'll stay a symphysis with cartilage if you're not an anthropoid. But if you're an anthropoid, it will soon fuse together. That bone is fused together. So another anthropoid trait, an improvement in within our line over the strepsirrhines. It gives us a better ability in many of the environments in which we are at. Now, in addition, there are other anthropoid adaptations too. If you'll notice that you have a dry nose. Now, notice that you must have touched a cat nose or your dog's nose. They have wet noses, and the wet noses are termed rhinarians. And they have little curls of tissue in there called rostrums. They're actually curled up in there, which give them a lot of surface area. Animals with wet noses have very sensitive noses, and they can smell, which can have a much better ratio than we can. But you see, we've given that up for the dry nose. Dry nose gives some advantages, right? One, it's easier to produce, less calories involved into it, and our brain doesn't have to commit as much energy to the sensory perception. We've offloaded the brain and focused on the eye, which is why up to 30% of our brain is really dedicated to vision. It's really strong visual acuity in the brain. We can see that in all anthropoids, and also in the nose too. We see, the dry nose that we have, as opposed to the wet nose the lower primates have, like all the strepsirrhines do. So another purely anthropoid adaptation right there. So when we talk about the evolution, the actual sequence in the fossil chain that we found, and how these things sort of reflect on their evolutionary changes, there are a huge amount of fossils. And to discuss just the fossil record that speaks to these events that are happening just in anthropoid transformations would require a 15 to 17-week course, which I would love to give, but this is a generalized course. We can't spend that much time on it. So what I've done is I've chosen some big benchmarks, some well-recognized benchmarks that illustrate something big that's happening in primate transitions. And most of these come from a genus called Eoceneus, a very early anthropoid. One comes from the genus Opidium. An anthropoid that's well developed within Africa that has a lot of evolutionary history in our line, and it portends to the rise of both the Old World and New World monkey groups. And they're going to be looking at Egyptopithecus. one of the precursors leading towards the development of all of the old world monkeys in Africa and around the world, as well as the rise of the great apes. Then in the next series, I'll be a little teaser here. In part number 3, we're looking at the genus Proconsul, which is actually the first transitional ape that happens 23 million years ago. So our time period for today really speaks from 45 million years ago for what happens to roughly just about 25 million years ago in the Miocene. So we're looking at 20 million years of time for the rise and the establishment of all of the early anthropoids, which are the old world monkeys and new world monkeys. And then after this point, after the 20 million year point we're looking at here, then we'll be looking at the rise of the apes. So what were the first anthropoids like? And where were they at? And who were some of the candidates? Well, there's a lot of candidates, but I think the leading candidate might be for this genus here called Eoceneus. And it's some of the remains have been dated way back to 45 million years ago, which is molecular evidence predicts that's where we should actually see a transformation of the primitive sort of haplorhine stock into the anthropoid stock. And this is about the point in which we get a split from the anthropoids into tarsiers. This particular genus is from southern China, which places exactly where we want to be, either in southern the Arabian Peninsula or in southern China. And we know that it's making radiations all over Europe. But we've got fossil remains in Pakistan by 32 million years ago. We certainly think that part of this genus could have established itself very early on in Africa, by 40 to 39 million years ago also. So it's part of a large adaptive radiation that could have very well given rise to all the anthropoids in Africa. So what does its name mean? Well, it was given a name that's very apropos. So Eo is Latin for dawn, and of course Simius is monkey, so dawn monkey, the very earliest stuff, right? The dawn monkey. And this is probably, what we're saying is it may not be the actual common ancestor, that exists right after the split of the haplorhines and tarsiers. This is the very first one that's moving towards the anthropoid line. This may not, but if it's not, it's really super similar to it. So it's a great benchmark. It's a great benchmark. So we've got something here that's very representative. And that's the way it is in the fossil past. There are very few sure things. There are some things we're going to look at. And I'll show you that are sure things. This one's highly ranking in the potential for a high probability, but there could be a shadow of a doubt here. Okay? We know something about the context where we find the fossil at, that it was likely highly variable, which we expect from anthropoids. Relied on insects, some of the nectars too, and some of the small fruits. There's very small fruits at that time and nectars also. And from sort of the patterns that we find in the fossils that we find, it appeared to be a very solitary creature. Now, this is odd because one of the hallmarks of anthropoids, and all the laundry list I've given you so far, one of the big hallmarks is behavioral hallmark, and that's sociality. We just love to be around each other for some reason. We don't like each other, but we're always going to be around each other. We need each other. In fact, our sociality is part of our success. Well, Eoceneus doesn't show that extensive sociality, and that's because, again, it's an early anthropoid going through these transitions. We're looking at anthropoids as we hit about the 33 million year mark. Things are going to change. That's when the complement of all these suite of adaptations come together. So let's have a look at Eoceneus. There's old Eoceneus right there. Now, I'll tell you, we're going to look at a genus that comes, comparatively close after this one, right, or more modern than this one, which appears in deposits right above it. And you're going to see a noticeable change in the body plan of this thing. So the body plan on this one's a bit narrow. Now, becoming an anthropoid means a little bit wider body plan. The chest area here, the breathing apparatus where your rib cages are, tend to be very ovular and long like this in many of the anthropoid groups. In apes, they're flat and they're wide. But the back tends to be a little bit more square in monkey groups. This still appears more cat-like in a lot of ways. Wouldn't you agree if you look at the overall body? But notice something. Look at the hind limb domination. That's one of the characteristics about anthropoids. They really show remarkable hind limb domination in their species. Now let's tax it. So the actual bones are larger, they're longer, and they're more powerful. So that shows the hind limb domination that anthropoids are really getting at this point. Now, next will be the facial features here, and that's very difficult to see from a side of profile view. But when you look at the head on, we're going to look at something different, something appearing here that will place it on the anthropoid map. Let's go look at what Chris Beard said. I think he's reiterating some of the stuff I've talked about. Let's see what he says here. So he says getting into Africa was at least as important as getting out of Africa. All right, so that's important because Africa will be the big engine. It'll be the big engine that causes a lot of changes in the anthropoid line, lending the ability for them to split into apes and finally into humans. Africa is where the actions, is where the climatic action is at. And it's not anywhere else in the world. So we're going to see that pretty soon. And that's because, again, it was like a continent within itself, sort of isolated. So none of the stuff that you see today, like the lions and cheetahs and giraffes and rhinos, originated in Africa. They're Asian imports. So the animals that did live in Africa, by the way, the elephant, I'll give Africa credit for that. The elephant originated in Africa, and then it adapted and migrated into India once the continents made full contact, and there was an isthmus that was able to do it. I want you to think about this. The differences between the African elephant and the Indian elephant. There are morphological differences, physical differences. You can tell the difference. I mean, size-wise, the African elephants are enormous, much larger. The behavior is much more aggressive. All sorts of differences in behavior too. So think about what Africa can do, and leaving Africa, the changes that can happen because of the different environment in which you're in. So when creatures like Eoceneus get into Africa, we're going to see all sorts of different changes, both in the structure of the body and in the behavior. So now let's have a look at Eoceneus face on. So here at the bottom, we have that traditional sort of profile view. And I love the way they put these, Eocene sort of forests together. This would be a typical habitat, and this sort of flowering plants that Eoceneus would be eating. You don't see any large fruits here. There's nectars and tiny little fruits, which sort of illustrates that anthropoids are going to get larger through evolutionary time. As the forests get larger and as the food supply gets larger. There's a 1-to-1 correlation, again, to the animal body plan size and actually how many calories are available in its environment, and what size of body a creature needs to negotiate the environment. So bigger trees mean bigger body plans necessary, but you have to have a greater food supply, which the trees will supply by supplying more fruits. So there's a coevolution that's happening here between flowering plant, and our anthropoids we'll see. And that's what's driving the trajectory of anthropoid evolution towards larger body plans. Now let's look at the face of these things right on. Something is distinct here. You're not looking at a cat or a traditional mammal. You're looking at something that has much reduced prognathicism. So if we look at the more primitive structure hindline, and we look at the haplorhines, and the haplorhines are going into anthropoids, there's only another direction the haplorhines go. That's the tarsiers. So essentially, when we're talking about haplorhines, we're really talking about anthropoids. So when we're looking at haplorhines, look at the reduction of prognathicism. Now, if you look at a strepsirrhine, I don't have a picture here, but we will look at them soon. Lemurs and lorises have a lot more prognathicism. And of course, you have that wet nose. Lack of prognathicism, dry nose. And the eyes, man, they are closer together, and they're out front here. They're out front. And you see how much the face moves out and is round here. That's a bigger jaw muscle, bigger mastication hardware. Bigger. And bigger heads. And more upright. Anthropoids are far more upright. Even when they walk on ground, far more upright. And they're more intelligent. They have larger brains per body size than strepsirrhines do. When it comes to intelligence, the haplorhines have it. Of course, there's a progression, as it increases from monkeys to apes and finally humans, which you don't see in the strepsirrhine. So, the thing about Africa and the evolution of Africa animals, all of them, including the primates, it's driven by continents. And it also creates a mystery for us. As our continents continue moving around the world, orogeny happens and mountain groups begin to appear because of continental thrusting together, changing all sorts of weather patterns. It also creates a mystery for us about how anthropoids get into South America. So we know that the common stock of anthropoids, is in Africa by about 40 million years ago. And by 36 million years ago, we get some fairly well-formed, proto anthropoids The characteristics that show in both populations, which are in South America, and characteristics that show in populations that are still in Africa today. So we think the apical ancestor between all South American monkeys and the apical ancestor, the same ancestor for all the ones we see in the old world, occurs in Africa at just about 36 million years ago. Because that is a time in which it's plausible that monkeys could have made it into South America through the rafting system, which I discussed earlier. Trees fall down through storms. Anthropoids are in them. Their food supplies with them, fruit trees. They washed out of rivers and they just drift across, seas and oceans into a new continent, the one that is moving away. And at just about this time, at 36 million years ago, we figure that there is a couple of 100 kilometers, but the prevailing wind systems were probably going to be, east to west. And, a tree loaded with fruit not only provides the calories in which a primate needs, they also provide a tremendous amount of fresh water. So that is a trip in which things like primates can make, and which things like elephants and lions and tigers cannot. And additionally, when continents begin to separate, it's never a clean break. They leave all sorts of uneven island systems and volcanic systems happening behind them as they spread. So it wouldn't be a long distance migration. It would probably be one by short hops that could have taken 20 to 30 to 50 to 100,000 years to actually make, chance trips aboard these rafting situations. But it's something that we've seen with other species before in other island communities on speciation. Things are out in the middle of the Pacific with all sorts of, things that shouldn't be there. But we think it was plausible just about this time. There's argument about the timing and when it happened, but I think 36 million years ago is a rough sort of timetable in which we can use in this class and be fairly accurate with some degrees. I'll be surprised if it actually changes as if more evidence comes along. So, in Africa, just about this time, who might be that candidate? Who might be the apical ancestor to, all of the South American monkeys and the the older monkeys, right? Which are Africa, parts of the Middle East, Indonesia, as well as Japan. And of course, the New World monkey group, they go to South America. Once again, they're ranged from southern Brazil up to about southern Mexico, really Veracruz, a few, but mostly it's in the Yucatan Peninsula, right? So what do we think? Well, right on top of, creatures such as, Eoceneus and deposits which are a little bit more recent, we something more well-formed. Now, look at the body plan here. This is different than what you're seeing in something like Eoceneus. What Eoceneus was a nascent early anthropoid. Look what we've got here. So Eoceneus was very small. We're talking maybe, 16 centimeters, maybe 9, 10 inches, something like this big. Now we've got something that's running 16 inches, 15 to 16 inches, in length and height, 25 to 30 centimeters. Look at the proportions of the body, but wider. The limbs are much longer. The head in geometry is much bigger, right? Look at this. And the eyes really well formed and forward facing. Large jaw apparatus here. This is a much more powerful creature that we have dating here. Now, we find its remains in a deposit along the Nile River in the Sahara Desert, right in Egypt, that's called the Fayum deposits. And I'll show you what that looks like now, but this is what it looked like then. Remember, Africa is always changing. I talked about it being, constantly under plasmatic proportions. Let's have a look at that. Let's have a look at how this fruit and insect eating primate, they were just picking up this fruit, a larger body, adapted for walking on the top of the branches. How did it arrive, and how are things changed since? I give you the Fayum deposit. There you go, modern day Egypt. Okay. Shows you the climatic changes that are happening. They're causing species to do all sorts of things that aren't going to be happening in South America. We'll see. Well, what's interesting here, why we love these Fayum deposits, is because the system here, the Lacustre River system, is one that's been around for a long time. The whole Nile Delta, oh my God, we're talking about something that ranges back probably maybe 40 million years. And it has sort of the same flow patterns, broad and wide, rivers raise up, pick up the silt, low energy, rivers drain away, drop silt, drop sand and silt deposits. Thus, for creatures which die along its bank, this is a low energy covering of sedimentary deposits, which means a high preservation bias. We get lots of fossils in really good condition. And they're on good palimpsests. undisrupted palimpsests of time. So we can see the chronological order of primate development. And Apidium comes along at just about that 36 million year point, just after we think a few million years after things like Eoceneus from the old world come in and are ready to make a split between the old world and new world groups. So Apidium, what tells us? What's something we know about this, right? Apidium. Well, first let's talk about some traits of old world monkeys, which you and I are an old world monkey. Let's just look at one trait. Let's look at our identiformity. So our identiformity is this: it's the pattern of teeth. We take it from just one quadrant of mouth. So if you take your mouth in half, you have upper and lower. Now we've got to divide it between left and right. So 1, 2, 3, 4 quadrants. Let's look at one quadrant. What are the patterns of teeth that we see? I have 2 incisors, I have 1 canine, I have 2 premolars, and 3 molars. So what's the pattern? 2, 1, 2, 3. 2, 1, 2, 3. So I share that with every ape on Earth right now, and I share that with every single old world monkey, without exception. We all have the same identiformity. All right, what about the monkeys, the anthropoids in South America? They're currently there now, but their case is different. Their identiformity is this: they have 2 incisors, they have 1 canine, they have 3 premolars. See, they have an additional 3 molar and 3 molars. So the identiformity is 2, 1, 3, 3. In fact, they have the maximum number of premolars allowed. Remember, a primate can have no more than 3 premolars. Well, they've got it. So the difference between us and them, one of the characteristics is 1 premolar. Well, what about Apidium? Well, Apidium has a 2, 1, 3, 3 premolar. All right. What does that tell us? It tells us it's the apical ancestor. Because if Apidium was the major form, it was in Africa at that time, which we see in the fine deposits. There's a huge amount of it, right? It's all over Africa. That means it can make that rafting trip into South America carrying that 2, 1, 3, 3 dental formula with it. And that's a founding population. Then South America moves away and develops all of the real monkeys. Well, how does that become us? And in the deposits right on top of it become another transitional forms that move away from Apidium, which we call Egyptopathecus, where the tooth loss has occurred. And because that's really the only thing we see there as far as anthropoid-wise, that change is so instantaneous. It's so positive. It hits all the species of anthropoids. And the anthropoids that don't have the change are, of course, greatly lose out because it's so positive, for anthropoids themselves. To not have that mutation really hurts any of the other species of anthropoids that are out there, and they're quickly put to extinction. Well, let's look at the creature that has that change into it and talk about why it was such a profound change. All right, so here we have Apidium. I want you to look, P133, and that predates the split. Now let's put a technical term on here. Old world monkeys, we're going to refer to those as platyrrhines, and new world monkeys, as you and I, are catarrhines. You can see yourself as a catarrhine. It has a lot to do with one of the diacritics. It's just look at your nostrils. They're ovular and they face downward like this, like this. New world monkeys are platyrrhines, flat. Their nostrils are ovular also, but they face outwards like this. All of them are all ovular. And all of the old world monkeys are like this, downwards. So if you look at a girl, they're like, oh, look at his nostrils are pointing downwards. That links you to all of the catarrhines, as well as your 2, 1, 2, 3 dental formula, but not this guy, 2, 1, 3. Not us yet, right? So here we can see a little bit of evolutionary action that's happening here, and then we'll interface it with the cast of characters we need next. It's the next thing that comes after Apidium coming the direction of old world monkeys. So who is it? So we have a common anthropoid beginning, right? Sort of in the, the middle of late Eocene there, which we saw, like Eoceneus is a pretty good representation of that. We go through a couple of transitional periods, and all of a sudden there's Apidium right there in the Oligocene. The Oligocene with the 2, 1, 3, 3. And then we can see it gives rise to You know, all of probably the South American monkeys, which we can see over on that side, right? The old world group. But in the center group, those are the old world monkeys. And right on top of that, we see a new species called Egyptopithecus. Egypto, right, is exactly where we find Opidium, right? Same sort of deposits. And Egyptopithecus has something very profound in it. And then it will go on to make transitions, of course, into the ape groups and finally into humans. So let's have a look at Egyptopithecus. Okay. Well, before we do that, let's think about something else. So Egyptopithecus, how profound a change is going to be and when it's going to happen. So Egyptopithecus comes along, roughly, 32 million years ago or so. And the first thing Egyptopithecus does, it begins to split off into two different groups. Once it's formed, once we have the very first old world anthropoid, the old world monkey, but bam, it makes a phylogenetic split. It does it. And one arm of the split produces all of the monkey groups we see in the old world now. We see baboons, we see macaques, cercopithecus, proboscis monkeys, big long noses. We see colobus monkeys, and that's it. That's the basic groups in which we see. Those are the old world monkey stock. And then the split that goes in the other direction begins the formation of the apes, which begins right at the beginning of the Pleistocene, just about 25 million years ago. And we'll be looking at this transitional creature called proconsul. That'll be coming in the rise of the apes. That comes next, okay? As they establish all of the great ape groups, the gibbons, saimangs, the orangutans, the gorilla, chimpanzees, and finally the beloved human. So just remind yourself where we're at right now. We're just about to make the transition into our superfamily, okay? So the catarrhine had been established. Okay, the old world, new world monkey is right there. Well, sorry, we're looking at the parvulary. We're looking at the anthropoid. The platyrrhine and the catarrhine has just been established. Okay, and by catarrhine, we're going into a different direction. It has to be represented by a fossil, and the fossil we're going to be looking at is Egyptopithecus, and that establishes our new parvulary. So here we go, Egyptopithecus. Yes, it means Egyptian monkey. Okay. It's the first with a 2123 dental formula. I'm so grateful because you're looking at grandma, how lovely grandma is. And that really is the proposed ancestor of old world monkeys and hominoids, all the apes. Now let's look at something else that is striking. So the gentleman here is holding, when it's his right hand he's holding, Egyptopithecus. Now compare that to the other fossil, which is Opidium, which is in the deposits right below. Look at the shift and change. Didn't I tell you guys there's increase in size? As things are evolving and developing in the canopy world, the anthropoids are getting bigger and more profound. Look at the facial characteristics. You look at the lower part of the face here, how more robust the bone structures are, right? And more forward facing. The eyes are more forward facing. Just this thing is becoming more anthropoidal. The dentition is larger teeth, and actually a little bit thicker enamel, Of course, we're going to see a more profound thickening once we get past the apes. But it really is, developing, more anthropoid characteristics. But now let's ask ourselves, why lose the tooth? Why lose a tooth? I think I mentioned it before too, but we have to think about it. Losing that tooth creates a bigger visual field, right? That's just it. And that's where it's at. That's how adaptive it is. If you've got a lot of prognathism and you're in an arboreal canopy, think about what you might miss, not only food resources, but other branches. How much of an advantage to have a reduction in prognathism by just losing one premolar, with further retracting the face, gaining another hallmark of anthropoids, loss of that tooth. And it allows the other teeth to get thicker and stronger for eating even more brittle foods, to increasing the breadth of the diet, becoming more generalized. So by far, the anthropoids that we see, as they develop in time, are becoming far more generalistic in their food supplies that you're going to see in the Strepsirrhine line, far more generalized. And Strepsirrhines, because they're very specific for foods within their niche, means they're very vulnerable to niche change. And that's why anthropoids represent really a larger proportion of the primates on Earth right now than the Strepsirrhines. So Egyptopithecus, just to represent how big he's getting. Check this out. Some of these specimens are 36 inches long. I mean, compare that to something, like Opidium, which is below, which is maybe 18. We've almost doubled size here. What a major adaptation. These things are gaining size because it's such a hit and such a success. Reduction in prognathism, the thickening of the enamel. Trees are getting larger. This thing's able to adapt to it. We're taking off. Egyptopithecus is the time in the heyday, right, of this major adaptation that's going to happen in all the different sort of forms of old world monkeys. This provides the base plan for that. It also provides the base plan for something that's going to happen too, the split towards the apes, because the apes are going to be building on this anatomy. This anatomy has to be here before we can have an ape transition. So thank goodness for Egyptopithecus. Now, where we go from here is the discussion of part 3 of this episode of primate evolution. And before I go, though, I'm going to mention one thing about Egyptopithecus, something very interesting that I find interesting, and things we can tell about it by looking at its skeletal anatomy. We haven't discussed a lot of this. I wanted to give you guys a brief overview of evolution, but if you look at the femur bone over here, this is the femur in the upper window here. You see the shaft, right, which is the diaphysis, right? And then we see the head of the femur, right? And then we see the neck, femoral neck that comes out, that connects it. Well, the angle here is changing. The angle is becoming greater. So the greater this way is increasing. So that means the femur is being tucked more underneath the body. Balance. But think about the way you walk. You put not your feet just in front of you, but more towards the center line, and that maintains balance for what you're walking is in the ground. Well, this maintains balance for something they're walking on, which are the branches. So, they're probably not a great leaping primate, but they're moving across the branches hand over hand, hand over hand. So a lot of, coordination between both the rear and the forehands are coming into effect too. Both of them are equally adapted. Not like Tyrannosaurus Rex with little fingers out here and well-adapted feet. I mean, both the hand and foot architecture are coming in strong together. I think about what you've got. Think about the adaptations in your hand. Well, that's responsible for a lot of the arboreal adaptations, right? Which really means quadruple head locomotion, hand over hand locomotion across the tops of branches too. And we can see that with the angled finger, the femur. It's very, very important. Now, next, how can we tell about what this thing is eating? Well, we look at its wonderful teeth here, which do reflect the 2-1, 2-3 architecture. Count them yourself. You see the 3 rear premolars and the 3 molars and the 2 premolars and the 1 canine. Well, the microwear, that's the smallest striations, and also the way the teeth glide around each other and movement and chewing. You don't think about it, but if you chew, there's subtle movements in the way you chew. And it depends, the type of wear you get will be depending on the type of food that you're eating. We can see this thing, eating a ton of fruit. It's a frugivore, and occasionally some hard objects also. So it's not purely a fruit eater. It's also, during periods in which fruit becomes more seasonal, able to fall back on other food resources. Broadening its diet, becoming a little bit more of a generalist, giving it a competitive advantages for animals who just, are consistent on one food resource only. Okay? The only thing this thing really needs is a good habitat. All right, so I'll see you guys on the next lecture, which will be the rise of the apes. Now, I'll leave you guys one more thing to say. Why not? We'll do it here. Let's leave off of where we're at so far. This is a little summary of what's going on. So here we have, Egyptopithecus. So you can see it visually giving rise to the first catarrhines, right? And first catarrhines supposed to be Egyptopithecus, right? And we're leaving the traditional world of the platyrrhines, which is marked by Opidium. Opidium sort of branches off into all the New World monkeys, and Opidium eventually goes out of business. It goes to extinction in Africa because Egyptopithecus is such an improved form. That 2133 and the changes in its body architecture put Opidium out of business eventually in Africa. Well, the ones that survive are in South America. Now I want you to look at something. Look at the amount of diversity and splitting, right? The phylogenetic splitting that we see that's happening in Africa among the catarrhines in the old world, as well as Indonesia, in parts of Japan, in the old world, versus the little activity that we see in the platyrrhines in South America. And that's reflecting on the climatic conditions, the constant upheavals that are happening in the old world versus fairly steady as they go in South America. Nothing really big has happened in South America besides the rise of the Andes in the last 40 million years, since it's actually began to move away, or 35 million years, since it's really started to move away. So without the engine, the climatic engine, and really changing stuff. Now we're getting changes in the populations of anthropoids, the newer monkeys, but they're not the major splits because we're not creating wholly new niches that can be exploited, right? So we're seeing drift and some subtle changes. So everything tends to stay together versus what we see in the categorizing groups. And that's what Chris Beard meant. They were just lucky to get into Africa. Because if they didn't get into Africa, the changes in which they needed to have to produce us humans never would have happened. Down there at the bottom, we would have not have occurred if the engine of Africa, the climatic thing, was not set into motion. Okay, I think I can leave off here. All right, so I'll see you guys through the next slideshow. Bye.